for disordered systems. Eric Donner is a PhD student who's leading the effort. Sorry.
It has to be done.
And this collaboration involves Anna Terleska from Middle Tennessee State and Kaming Tam and Juara Moreno from Louisiana State University. So let me just, my page turner. Okay. I'm having a hard time advancing my slides. Let me. I'm just going to have to come back and click. That's fine. So we could do that. So the interest in studying correlated systems away from equilibrium with these tools stems from many different questions, right? From the one hand, you have these trend of device miniaturization. And what that means is that you have devices that are getting increasingly smaller. And as they do, you have small potential differences that when you have these across very small distances, you have strong electric fields. And these strong electric fields are such that treatments using linear response theory will be globally inaccurate. So you have to come up with tools that allow for more accurate treatments of these. And of course, you have recent experimental advances in, say, pump probe spectroscopy, for instance, where you have a strong pump that's going to drive your system out of equilibrium, and then you'll have a weaker probe that then assesses the excitations in the system. And those non-equilibrium dynamics, non-equilibrium excitations in the system will teach you something about the underlying, the competing orders in the system that you have. And of course, you have the ultracold atoms in optical lattices, where you can, essentially the experiments themselves are intrinsically out of equilibrium, but also you can use these experiments to engineer a variety of non-equilibrium Hamiltonian and study their dynamics. For both of these types of experimental efforts, it's essential that you have appropriate theoretical and computational benchmarking techniques. And so this is kind of the space that we're looking to occupy with these studies. Typically, the questions that you will have will be, you have some state that you start off with at some time t equals 0, and you know what you're going to do to the system. But the question is, what's going to be the final state after you've produced a certain number of actions on your system? It's not so trivial for a quantum system. And of course, you can ask questions as, that long time state that you'll end up with, is it even going to be a thermal state? How long is it going to take, if at all, to reach a thermal state? So those are questions of interest in this research direction. Right. And on the other hand, I'm going to be talking about disorder away from equilibrium. Now, disorder is the rule rather than the exception when it comes to many particle systems. And even though we know that it produces a variety of intriguing behaviors, its role in the analysis of many experimental situations is typically kind of understated. And this is in part simply due to the complexity that arises from incorporating disorder in the analysis. It's just another layer of complexity that typically is out of reach with existing tools. So there's a real need to come up with capable tools that allow for us to treat, not just interactions, but also disorder, and possibly disorder and interaction. And this need applies both in equilibrium and out of equilibrium. In the context of the work that I'm going to be discussing here, we're going to be looking at systems that have both interaction and disorder away from equilibrium. So we're going to be studying the dynamics of correlated disordered systems. And here we're going to apply that in the context of an interaction quench. Now, the formalism in general is going to be dealing with models such as the Hubbard model. So you have something where you have some interaction. For W occupied side, you have a hopping amplitude between nearest neighboring site. Your hopping amplitude, typically here we call it J, just to not confuse it with time. You have your chemical potential, you have your Coulomb interaction. For the Hubbard model, typically the hopping amplitude is the same for different spin species. Whereas if you have one of the spin species that's fixed on the lattice, and you allow the other one to hop, you're left with the Falikov-Kimball model that characterizes also a mixture of heavy and light particles, where the heavy particles are glued on the lattice and the light particles are allowed to hop. And in terms of the non-equilibrium dynamics, we will often be interested in putting on, say, an electric field, say a DC field that is switched on at some time t0. Or we can also look at a pulse field where that electric field has some profile in time and is applied to the system. We often also look at interaction quenches where we start off with some interaction strength U equals U1, and at some time t0 we switch from U1 to U2 in an abrupt manner, and then we ask what's the dynamics of the system following that abrupt change in the interaction strength. Now, for the many-body formalism away from equilibrium, the fundamental challenge is that we have a violation of the Gelman-Lowe theorem, which typically tells us that the state of the system in the very distant future is connected with the state of the system in the distant past. In other words, what you do to treat your interaction is that you adiabatically turn it on and you adiabatically turn it off. So the state of your system at plus infinity is just a phase factor multiplied by the state of your system at minus infinity. Now, if you're away from equilibrium because, of the non-equilibrium dynamics, this is not going to be true. And so what that means is that you have to use the Krenov-Baim-Keldysh formalism, whereby you evolve the system forward in time, but then you evolve it back in time to reconnect with the initial state that you know. And that is then going to allow for you to assess physical properties of your system up to some time Tmax along this contour. Now, if you have a system that's initially equilibrated at some temperature T, then you add a vertical spur on this contour to be left with this kind of L-shaped contour. And typically, of course, we're going to discretize this time contour according to some delta T spacing along the horizontal branch, and also possibly some different spacing along the vertical branch. And so that gives rise to your Green's function now having this kind of texture, right? Where if both times involved in this Green's function are on this forward branch of the contour, this is what you have. You may also have one time on the top contour and another time on the lower contour. This is what you have. You may have one time on the top contour and then another time on the vertical spur. This is what you have. So in general, this is going to be your contour-ordered Green's function. So you may formulate the many-body solution either in terms of this contour-ordered quantity, or you can go back and rewrite the many-body formalism in terms of the different types of Green's functions. So the lesser, the greater, the retarded, the advanced, and the list continues here with the mixed Green's function with one time here and one time here, or with both Green's functions here, the Matsubara Green's function. So you can write that formalism in terms of involving all these different Green's functions. But alternatively, you could just use the contour-ordered Green's function. This contour-ordered Green's function approach has the advantage of being very similar to the equilibrium approach. Now, it also has the two different ways, the two different solutions will have different challenges. For instance, the contour-ordered quantity will require more memory in the computer, whereas with the different Green's functions, you only have to store each of them in memory individually, and your linear algebra is then going to involve smaller size matrices. However, what we found is that typically one can go pretty far using the contour-ordered Green's functions, certainly with the type of computers that we have at our disposal these days. And then once you have then this two-time Green's functions, the way that you're going to do the analysis is to change your coordinates from the TT prime coordinates to the T average and T relative coordinates, right? And so this is then how you're going to analyze your system, because in these terms, T average then becomes kind of like an effective time for your system, whereas T relative is the thing with respect to which you will perform your Fourier transform. So if I want a time-dependent density of state, I'll do a Fourier transform with respect to the relative time, and this is going to allow for me to track the time dynamics of the system, right? And typically then, you get all your physical observables from the contour-ordered Green's function. The retarded Green's function, for instance, is going to give you your density of states. The lesser Green's function is going to give you the distribution function. And from these Green's functions, you can extract all the observables that you care for. The current, the kinetic energy, the potential energy, and so on. You can calculate all these observables from the Green's functions. Now, how does DMFT go then about solving this formalism on the contour, on the Keldysh contour? What you do is you take the lattice problem and you map it onto an impurity that's embedded into a self-consistently determined bath. And so this impurity problem becomes what you have to solve. This mapping, of course, is going to lose some of the non-local fluctuations. However, by construction, DMFT is going to allow for you to capture the time dynamics on this impurity. The challenge then is, how do you solve this impurity problem? And there's a variety of tools that one can use to solve the impurity problem, right? Starting with quantum Monte Carlo, exact diagonalization, diagrammatic methods such as perturbation theory, non-crossing approximation, random phase approximation, flex, and so on. We also happen to have in our hands a model for which we can write this impurity solver exactly analytically. We have an analytical solution for this case. And this, again, is one of the advantages of the Farikov-Kimball model. Not only is it going to allow for us to study mod physics, but it also has an analytical solution in this context, which is quite an advantage. And then you can apply your non-equilibrium DMFT to a variety of problems, and this has been done in the literature. Folks have done field-driven system interaction, quenches, spectroscopy, and so on. And by the way, I'm okay if folks want to interrupt with questions, or if we want to delay until the end, that's fine too. So this is just a little bit of a snapshot of some of the work that has been done using non-equilibrium DMFT. There's obviously plenty more that I can list here. So I'm going to go ahead and discuss some of the applications that we've made with this approach for the field-driven systems. And in order for us to get a clear picture of how the field-driven behaves, I'm going to start by talking about the Farikov-Kimball model in equilibrium, right? So if I take the Farikov-Kimball model in equilibrium, and I look at its density of state as a function of the interaction strength, starting from left to right, weak interaction to strong interaction, what you see is that you start with some simple, boring Gaussian, but as you crank up the interaction, you get the opening of the gap, and that occurs in this model at u equals square root of 2. And so that's what you have for the Farikov-Kimball model in equilibrium. Now, you can ask about the typical many-body system, what happens in the steady state when I apply an electric field? And that question is, you can ask that question independently of what the transient is, right? You say, I'm not going to worry about the transient. I'm going to say, okay, let me study the steady state of the system. And you can formulate DMFT to address the steady state without worrying about the transient. And in that steady state solution, you can calculate the densities of state of the Farikov-Kimball model. And so you repeat the calculation that I've just shown for the same interaction strength, and you see a much richer picture for the field-driven system than for the equilibrium system. When you turn on an electric field, you have the well-known Vanier stack ladders that have essentially delta peaks at delta function peaks at even multiples of the electric field strength. And those peaks will broaden as you crank up the interaction. You'll broaden and then they will merge. But then you will actually get the opening of the gap that's delayed to much stronger interactions. And even when you do get the opening of the gap, you will have the creation of in-gap states as a result of the applied electric field. And so on the top picture, I'm showing a weak electric field of weak 0.5. And here's the field is stronger, is 1.0. And here everything is measured in units of the hopping amplitude. And so you can see consistently this picture in terms of the Vanier stack ladder, the broadening with the Coulomb interaction, and the merging of the peaks, and eventually the opening of the gap, but then the formation of the in-gap states. Remember, your mod gap would be between these two peaks here. But now you have the formation of these sites in these states in the middle of the gap.
May I ask you how you study directly the steady state? How to introduce the electric field?
you can formulate this like a Floquet
Oh,
driven
okay.
system.
All right.
Yeah.
Okay. Got it.
Mhm, mhm. And so then, you have an equilibrium system, you have a solution for the density of state, and you go to the steady state, you have the density of state. Now we can come back and ask, okay, what's the dynamics that happens between that equilibrium system and that long-time steady state that we have now characterized and understood? What exactly is it that happens in the system between the equilibrium and the steady state? So, well, if you apply the electric field, we know we're going to have an electric current, right? If you have no interaction, we know that that electric current is just going to be oscillations, block oscillations that persist forever for no interaction. But as you turn off the interaction, scattering is going to lead to the decay of that current over time. And so that's what you see here. You start with the equilibrium system, and the field is going to be applied at the end of this horizontal branch at t = 5. The field is applied here. So you get the onset of the current, but that current decays gradually as a result of the interaction. Now, if you tune these parameters, you'll see a variety of different ways, different mechanisms through which this current, starting from 0, decays over time. In some situations, you get this oscillatory behavior. In other situations, you get a collapse and revival of the block oscillations. And the revival of the block oscillations will occur with a period of 2 pi over u, u being the interaction strength. In other situations, you get just a simple monotonic decay towards 0. Now, this monotonic decay towards 0 is also well understood. Say you have an isolated system, you put an electric field, the current starts flowing through the system, but as it does, you get Joule heating. So your system heats up. You start from an initial temperature, the temperature increases until it becomes infinite. Infinite for the purpose of the system, meaning that all K points, all momentum points are equally likely to be occupied. So you get as many particles flowing to the left as you do going to the right, and so the current vanishes. So that's what you're seeing here as the current is going to 0. That's the picture, the physical picture in these systems. And so then you can ask, can we better characterize this transient dynamics, this relaxation towards the steady state? At half filling, we know that the real part of the retarded Green's function should be equal to 0. We also know that if we have a thermalized system, we should have the fluctuation dissipation theorem. In general, we also know that this property applies at half filling. So we look for the validity of the fluctuation dissipation theorem as a measure for whether or not the non-equilibrium system is thermal, right? And we'll also calculate different observables and see how they behave as a function of time. We know if this system is going to an infinite temperature state, we know what the different physical observables we're interested in. We know what their values should be. So we can ask, how do we approach those values? And so this picture here tells you some of the different scenarios of relaxation that we observe. We will see scenarios as a function of the parameters where you have a monotonic thermalization, monotonic no thermalization occurring. In other words, the current is decaying towards 0, but everything else doesn't seem to be going to its final infinite temperature state. So it's conceivable that that long time state is non-thermal. You will also have scenarios where these two behaviors are oscillatory. And how exactly do we classify this? Here's an example. For the case of the monotonic thermalization, like I said, the real part of the lesser Green's function for a thermal state should be 0. Here we see that it decays monotonically towards 0, as captured by this maximum that decays monotonically. We look at the different observables. Here's the infinite temperature total energy. And what you will see is that you gradually monotonically increase towards it. The current itself is going to be monotonically going to 0. So this is just a snapshot of the analysis that goes into categorizing these different relaxation scenarios. And then, of course, you can go and look at the imaginary part of the lesser Green's function and see if it obeys the fluctuation dissipation theorem. And what we find is that indeed, for this case of a monotonic thermalization, after a short time transient, immediately we can fit the thermal distribution to the ratio of the retarded Green's function by the lesser Green's function. And this pretty nicely follows the fluctuation dissipation theorem up to the latest time achievable by the simulation. Now, in blue, what you see here is the long time, the infinite temperature the infinite temperature quantity, which we cannot achieve through these simulations, but we're coming pretty close already. And so if you understand these pictures very well, and if you understand what's going on, you may be able to extrapolate the physical properties of your system between the transient and the steady state, and essentially have a full characterization of the dynamics of the system. So this is something that is pretty nice to see. And I think here is where I'm going to shift gear and talk about the disorder studies away from equilibrium. All right, so for the disorder studies, what we're going to do is first start by looking at, historically, the tool that has been used to study disorder in the many-body field is the coherent potential approximation. And if you look at the algorithm for CPA, it's very much similar to the algorithm for DMFT. It is also just constructing an impurity problem and solving that impurity problem for in the case of disorder, now you have to solve that impurity problem for different configurations of your disorder. And then you have to do this disorder averaging for CPA. But otherwise, the two algorithms are quite similar, right? So between your DMFT and your CPA, the similarity are pretty transparent. So what this also says is that we're able to merge these two algorithms pretty well. Now, CPA as it is has already been extended to non-equilibrium. I've already told you that DMFT has been extended to non-equilibrium, but so has CPA for systems that have disorder but no interaction, right? And it's been applied to this type of mesoscopic devices where you have some leads and in the middle, some system that has disorder on-site energies. So what we want is to treat both the disorder and the interaction away from equilibrium consistently. And both DMFT and CPA allow for us to do that. And this is the algorithm that we're going to be using. So essentially, we're just combining DMFT and CPA, right? Except for every G script that you have, you're going to solve for the self energy for a given configuration of the disorder. You will then obtain the Green's function, and then you'll do a disorder average over all your disorder configuration before proceeding to do your cost grading and coming back and repeating this process. This sigma that we have here is then a correlation sigma. So here you're solving, say, for, perturbatively as a function of the interaction strength, or you're doing Monte Carlo or anything like that, right? But then you come back here and then you repeat that for all, you're doing this for all disorder configurations, right? Okay. And so this is the algorithm that we're going to be applying to study disorder. Except we're going to be doing it away from equilibrium once again. And the model, the typical model for disorder is going to be the Anderson-Hubbard model. So you have still your hopping amplitude, you have your interaction strength for doubly occupied site, but now you have this V, which is a local energy, which is going to be different across the different sites in your system. And that distribution of the V is going to be following this probability distribution. In our case, we just chose it to be this box distribution. So it's a flat distribution, essentially, between some minus W and plus W. And so W becomes what we call the disorder strength. We're going to be studying this for an interaction quench. So we take this model that has U and V, so a model that has interaction and disorder, and we keep the disorder strength the same, and we quench the interaction from some initial value to a final value. Our initial value is going to be 0, so we quench from non-interacting to interacting with strength U. And we're going to be studying the long time, the dynamics of this system. Now, given this formalism, you might want to first benchmark it against results that we know. And so this is what we started by doing. First, this is once again the algorithm. I've already spelled this, so I'm not going to expend too much time on this. So you have your G script, you solve your self energy, your interaction self energy, and then you do this for all disorder configurations. You do disorder averaging, you extract your hybridization, and then you come back and then you repeat until you converge within some desired criterion. Note that the hybridization here is what you do. We're solving this for the beta lattice. So that's why we're able to have this exact expression for the hybridization in terms of the average, the disorder average Green's function. This solution, of course, is going to recover DMFT if you have a clean system, if you don't have disorder. It's going to recover CPA if you don't have interaction. And so that allows for us to readily do the benchmarking that we're interested in. We're going to calculate the density of state for a model with disorder and without interaction. We can compare that to a CPA solution. And what we find is that indeed our solutions agree pretty well with the CPA solutions for a non-interacting system. So for the Anderson model for disorder, we have pretty good agreement. Of course, you will have this type of Gibbs phenomenon because you have these sharp edges and you're doing a time domain calculation and then Fourier transforming. Because you have this truncation in the time domain, you'll be left with this Gibbs phenomenon. So that's something that we understand. That's an artifact that we understand very well. Right, so we have a pretty good agreement there. And we can then shift gear and go to the Anderson-Hubbard model where there has been some calculations for this system, for the densities of states of this system. The exception here is that we're going to do this calculation with the time domain, with the time domain formalism. And so all we do is a Fourier transform. We're not doing any analytical continuation or anything like that. And so this figure is showing you the densities of state for different interaction strength as a function of the disorder, And what you will see is that for weak interactions, what your disorder does is essentially to smoothen out your density of state. And that picture persists all the way up to where you see for U values where you would in principle have the opening of the gap. Now, as you crank up the disorder strength, what you find is that the disorder fills up the gap. So you get an insulator to metal transition that's induced by the disorder. And this is also in agreement with some previously reported calculations. Once again, one key advantage of our solutions is that there's no analytical continuation. So you can imagine being able to readily apply this and just doing a Fourier transform and getting densities of states that are not really subject to much approximation except for what your impurity solver is. Okay. So this was for the benchmarking. So now we're going to do the dynamics of the system across the quench. We're going to calculate different observables and look at their relaxation. For this particular problem, the observables we're going to be looking at will be the kinetic energy, the potential energy, and then the total energy. Now, what happens when I'm performing an interaction quench? On the left of the interaction quench and on the right, I have an isolated system. When I quench, the energy should then be constant on both sides of the quench. And so the total energy of my system should be constant. That's a nice thing to know so that you can then assess in terms of the capacity of your solution, right? And then we're also going to look at the Wigner distribution function for this problem. So here, I'm showing you the relaxation of the system for different interaction strength in the different panels. And each of the panels, I'm showing different disorder values. And so what you will notice is the different behaviors, across the interaction, the different interaction strengths. So let me look at U equals 0.25 and U equals 0.75. What you will notice is that you don't have as much variation as a function of the disorder strength at weak interaction as you do for strong interactions. Now, in panel D, what you're looking at is the breakdown of our solution. And this is nice to document because you're looking at an energy that's supposed to be constant, but it is clearly not constant. You're looking at a relaxation that's not actually happening. So this shows just that away from equilibrium, our formalism that's in this case based on second-order perturbation theory as an impurity solver is breaking down. And so one of the next things that we're looking to do is to implement solvers that allow for us to go beyond moderate coupling. And here the units of energy here are such that the hopping is 0.25. So this essentially is four times the hopping where the solution breaks down. Okay, so we're able then to take this solution and then ask, how are the states occupied? What's the distribution of the particles across the states in the system? And so that's what you do here when we calculate N, is essentially the distribution, the Wigner distribution. And we calculate that as a function of disorder strength across the quench. And so what you see is quite interestingly, that at weak interactions, what you see is that as you increase the disorder, you get a higher temperature. Whereas at strong interactions, as you increase the disorder, you seem to get a lower temperature, and that's kind of puzzling. So that's something that's, the subject of ongoing studies. And we've had some, kind of new results lately that are not yet published, but I'm very excited to share those with you. And that has to do with actually calculating the thermalization of the system, right? So I can calculate the effective temperatures. And to get the effective temperatures, what you have to do is you have to get those retarded and lesser Green's function. You have to Fourier transform them. And then you have to apply the fluctuation dissipation theorem. And your fluctuation dissipation theorem requires that you use a distribution function. Okay, so once I get these two quantities, I can take the ratio of them and see if it fits the Fermi-Dirac distribution function. And so that fit gives me a temperature, and that's going to be the effective temperature of the system. Now, it's not always going to be possible to perform this fit. And when it's not possible to perform this fit, we'll say that we don't have a thermal system. So indeed, we will assess whether or not the system is thermal based on whether or not we satisfy this fluctuation dissipation theorem. And in terms of taking this ratio, one also has to be mindful, because your lesser Green's function, your Green's functions in general are going to be decaying away from the Fermi energy. And so you can't take the ratio away from some minimal value, because you just have too much noise. You're dividing things by zero, and things are not going to be well behaved. So one has to be mindful of that. So we define a window around the Fermi energy for which we're then going to calculate this Fermi distribution function. And that's going to be to allow us to get the effective temperature. And this is what we get. So that's how we get these effective temperatures. And so in this figure here, I'm going to do the quench from u equals 0 to a final u, u2. And that's the value that's on the horizontal axis. For that value of u, I'm going to calculate what the final effective temperature is. And I'm going to repeat that calculation for different disorder strength. So at each u, what you're looking at is the different disorder strength for which I've calculated the effective temperature, right? And so what you see is a picture very similar to the, in agreement with what I just mentioned earlier. For weak interactions, you have the fact that your increase in u corresponds to having your increase in u corresponds to having a lower temperature, whereas here, what you see is that you're having a higher temperature. And another, one thing that's very important to point out is what this figure is also telling us is that the thermalization of your system, the final temperature depends a great deal on the disorder in your system. And that should be quite informative in terms of the analysis of spectroscopy type experiments that are typically based on a hot electron picture, whereby you say, okay, I have a system that's equilibrated at this temperature. I pump the system, so I add energy to it. It goes to an equilibrated system at some higher temperature, right? And so what this picture is telling you is, well, that final temperature will depend a great deal on how you treat the disorder in the system. So this is, a pretty neat result, we think. We're still polishing this up, and so we're looking forward to putting this out hopefully soon. And that was my kind of the last key result that I wanted to share with you. I will just basically leave my slides on the screen and take questions if there are any.
Thank you very much. All right, the session is now open for questions. So we're going to start with the live audience. Any questions? Yeah.
Whenever you were testing your combined method, is there a reason you chose the Bethe lattice?
One key reason is just convenience. It is the one lattice for which you have this easy expression of the hybridization as a function of the Green's function. And so that allows for us to readily implement the algorithm and check things.
Okay.
But of course, the algorithm is not by any means constrained to the Bethe lattice. In fact, we're looking to expand it to a hypercubic lattice.
Gotcha.
All right, I have a couple of questions, but I'm going to leave them for the end. Before we're going to ask the online audience to raise your hand or unmute yourself if you have any questions. No questions from the online audience?
Maybe I can ask a question.
Yeah, great. Please, go ahead.
So the DMFT that you're using here for the disordered case, this is a single site DMFT, is that right?
That's correct, yes.
I mean, is it possible to extend it to like small clusters to get a little bit of momentum resolution, or is that numerically too expensive?
It's numerically expensive, but not too expensive, and it's on the to-do list. If you look at the Outlook that I have on the screen right now, even though it's at the bottom of the Outlook, it's one of the things that are high in priority.
Mm-hmm.
I think it will be quite informative. That's a very good question. Yeah. Mm-hmm.
Mm-hmm. Okay, great. Yeah, thank you.
So this is a very naive question, but it's a good follow-up to Greg's. If you're using a single site formalism, how do you define a directionality or a current in your system?
Yes. Okay. So DMFT, formulated as an impurity problem, allows for you to calculate the lattice quantities. And so you're able to extract the lattice quantities. The main constraint is that the correlations are captured on the local site. So your self-energy, sigma of k, is just sigma of omega, so it loses momentum dependence. But then you can calculate the lattice quantities, right? So you can calculate all the lattice quantities with the same self-energy, essentially. So the dispersion is the only thing that gives you the lattice in that case.
All right. And another question, which is unrelated, it's something that got me thinking at the very beginning. It was one of the first slides that you showed. The work with Frerichs with on the steady state with the electric field. You said that you use Floquet formalism, but typically when people use Floquet for the steady state, they say it's basically in the high frequency regime where you can just take the effective Floquet Hamiltonian, and the only thing that it does is normalization of the hopping, right? But here you see all the replica. It's like you're actually doing all the frequency range. So you're not doing just averaging. That's
right. This is Floquet-like. It's not, crude Floquet, so to speak. Yeah.
All right. I'd like to learn more about that. So I guess I'm going to go and read your paper. There was a question on the chat.
Oh, let me see if I can open that. Maybe I missed something. Sorry if it is the case. Did you try some point analytical extension in the Keldysh approach to study thermalization effects? Analytical approaches per se, not on this problem. Certainly, I haven't. There's been some studies using analytical approaches, but typically the challenge, of course, is calculating the Green's functions and addressing the correlation effects. It's just kind of difficult to do that analytically. But there's some. You can say some things, if you constrain the reasoning somewhat using, say, fluctuation dissipation theorem, and say I'm going to look at the steady state only. You can say some things using mostly analytics, but in general, we've used numerical techniques, in part because we want to address these correlations and so on.
All right. Any other questions? All right. If not, I guess we'll thank Herbert one more time.
Thank you.